Okay, so we just learned about commutators. Let's now play around a little bit with these concepts. So say we have a linear operator A, and that operator operates on an input which is x. So x could be a vector or a function, whatever, doesn't matter. And it spits out an output y. So y is equal to ax. Okay. And then let's introduce a second operator, b, and it turns out that b actually commutes with a. So the commutator ab is equal to 0. And then I'm asking myself the question, what will happen if I have again my operator a, but rather than operating upon x, I'm now operating upon bx. And the question is, what will be the output? So pause the video and see if you can figure out the answer to this one. So what will happen is that the output is obviously a, but operating not on x, but on bx. So the output is a bx. But since we know that a and b commute, this will be equal to b ax. Okay. And from what we started with, we know that ax is actually equal to y. So our output is by. So interesting conclusion, if you have two operators which commute, that means that if you operate on x, you get y with a, and if you operate on bx, you get by. So that's a very interesting conclusion. And also bear in mind that never in this whole derivation have you actually made use of the fact that, for example, x is an eigenvalue or an eigenfunction of a. So we have derived something which is completely general, which does not depend on eigenvalues or eigenvectors, just on the fact that these operators a and b commute. But let's now take this one step further and let's see if we can, for example, be clever with trying to make use of the fact that we do have eigenvalues and eigenvectors, and see if we can derive the same result, namely that if we operate on bx, we get by as a result, but without relying on the fact that these operators commute, but by taking some clever choices. For example, by trying to see what would happen if, let's say, x is an eigen function of b, for example. Then we can sneakily get rid of this b here, and hopefully, if we're creative, we can also derive a similar conclusion that perhaps will only hold for very specific inputs, without making use of the fact that these two operators a and b commute. So try your hand at this and see what happens. Okay, so let's look at the output that we have. The output generally is a bx. And I told you, let's be creative and let's try to see what happens if we work with a very specific x, which is an eigenvector of b, so that bx is lambda bx. Okay. Now in this case, so we have a of lambda bx, and since our operator here is a linear operator, we can shift the eigenvalue to the left. So we have lambda bax. So now we no longer need to worry, apparently, here about the order of a and b, because it's just a multiplication with a scalar, and we can bring this outside the operator without any problem. We also know, if we go back to what we have here, that ax was our original output y, so we actually have here lambda b of y. Okay. Now, what we would really like to have is that we can also derive something similar, namely if a operates on bx, we get back by. So we would like to have that this thing here is also equal to by. So this is what we need to look at. So actually, if I rewrite that here, we need to have that by is equal to lambda by. Okay. And again, what is our y? Our y was actually a of x, right? So lambda bax. Okay. So now we're still a bit in trouble here because we have b and a, and here we only have a. So let's see if we can repeat that creative trick one more time. And let's now say that we also assume that x is not only an eigenfunction of b, but it's also an eigenfunction of a, so that we can here write that this is equal to lambda a of x. Will this help us further to prove this statement here? Well, let's see what happens. So we have then lambda a bx. Question, is that equal to lambda b? And then a of x, of course, is also lambda a of x. And we started out by saying that we had a special choice of x such that b of x is equal to lambda b of x. And then indeed, we arrived to the conclusion that the left-hand side and the right-hand side are equal by making some clever choices for eigenfunctions and stuff like that. However, what we've basically used here is we've used the fact that x is an eigenfunction both of the A operator and of the B operator. And we know that if they're operators which have common eigenfunctions, that basically means that they commute. So we try to be clever and get rid of the commutation operator, but still in the end, we had to use it anyhow, but more in a roundabout way. Okay, so this was just some playing around with the concepts of commuting operators.